Hello everyone, my name is Tongtong Xiang and I'm from the University of Waterloo. I will be presenting PUnits, a precise inference of expressive units of measurement type system. So why is the unit of measurement type system important? Performing calculations with mismatched unit can result in catastrophic failures. As an example, the Mars climate orbiter disintegrated in 1998 due to one software component communicating values in imperial unit, while the receiving component expected values in SI unit. This mismatch costed US taxpayers $327 million. Numeric computations can be performed with primitive types or abstract data types. For efficiency reasons, numeric computations are usually performed with the primitive types, but it provides no type safety guarantees. Abstract data types provide some type safety guarantees. In our evaluation, we'll show you how our type system provides a stronger static guarantee than using an abstract data type, while also having the performance benefits of primitive types. A less catastrophic example is a bug in Firefox from 2012, where Mozilla added a swipe to close feature to its Firefox browser for Android. A unit-related error in the implementation prevented users from activating this feature. Mean speed, or the initial minimum swipe speed, is the primitive integer with value 1000, and mean speed is intended to be interpreted as pixels per second. If a user swipes a browser tab with a speed exceeding this minimum, indicated as speed x, the code will animate the closing of the tab. This feature was updated to adapt to different devices by computing the speed with respect to the screen resolution in DPI. And DPI is intended to be interpreted as pixels per inch. But the mean speed was not adapted during the update. This led to a comparison between inches per second with pixels per second, and this unit mismatch disabled the feature. To effectively prevent such errors, we introduce PUnits. PUnits is a unit of measurement type system. It is expressive, precise, easy to use, effective, and sound. A user of PUnits can pick among one of the three modes: modular type checking mode, whole program inference mode, and whole program inference with annotation mode. I will introduce this mode in detail in the following slide. The type rules only need to be defined once, and our framework provides all three usage modes. We also have proved the soundness of the system in Calc. We will now introduce the workflow of PUnits. Developers can first provide partially annotated source code and library specifications as inputs to PUnits. The source code then gets parsed and normalized into a partially annotated abstract syntax tree. In modular type checking mode, PUnits uses defaults for missing annotations in the partially annotated AST. These defaults are chosen to give errors across method and class boundaries. A set of mandatory type constraints is then generated by syntax-guided constraint generation rules. And in type checking mode, every constraint is solved upon creation. And if all constraints are met, then we can ensure unit soundness. Otherwise, the unsatisfied constraints will produce compilation errors. The type checking mode provides developers a quick feedback on unit-related errors with a method local view of potential problems. In whole program type inference mode, instead of applying defaults, constraint variables are generated for the missing annotations in the AST, which are placeholders for concrete units. The mandatory constraints that are generated are the same as the ones generated in modular type checking mode. The constraints for the whole program are collected and solved together by a max SMT solver. Multiple type-safe solutions are possible in inference mode, and as long as a solution exists, then inference will succeed. If inference fails, then a set of unsatisfiable constraints are provided. This mode ensures a valid typing exists for the whole program. It pinpoints code locations across the program that together would cause a unit-related error. Annotation mode has the same workflow as whole program inference mode, but with additional breakable constraints, we rely on the SMT solver to produce optimal solution, guided by the constraints provided to the solver. Annotation mode inserts the inferred solution back into the source code, giving the developers a chance to inspect the result. And this workflow is intended to help developers create well-specified applications and libraries. PUnits represent scientific units as a single prefix and the product of one or more base units, each raised to an integer power. The base units are expandable and customizable. The qualifiers are organized as a flat lattice over the set of concrete units, with top and bottom type qualifiers. Top expresses any type, and bottom is used for null types. PUnit supports polymorphism of units via the type qualifier polyunit. The unit is computed as the least upper bound of the method receiver and argument. In the example, the assignment to variable bad gives an error because it requires the result to be a meter, but the method returns top. PUnits also support receiver-dependent units via the RDU type qualifier. It can only be used for return or method parameters to guarantee soundness. Any occurrence of RDU in the signature is substituted with the receiver type during the method invocation. In the example, an invalid argument type is issued because the method 2 nano requires second as argument, but the argument is nanosecond. All scientific unit types are encoded as 2 Boolean variables and a set of integer variables. Beta top represents the top type, and beta bottom represents the bottom type. Omega represents the exponent of base unit. Here we have some examples of how units are encoded. PUnits generates 3 kinds of constraints over types: the well-formed constraints, the subtype constraints, and the arithmetic constraints. Alpha is a constraint variable. The well-formed constraint enforces that any satisfying solution for alpha is uniquely interpretable as a single unit. As an example here, if both and bottom are true, then it is not uniquely interpretable. All constraint variables must satisfy the well-formed constraints. We show you the encoding for the subtype constraints as a constraint encoding example. The additional breakable clauses are enclosed in square brackets. Inequality constraints and comparison constraints are built upon subtyping. Now we go back to the Firefox bug. Placeholders 1 to 8 are used to mark the locations for which types need to be determined. The blue boxes are the expected unit for each variable. The red boxes are the constraint generated at each program locations. The developers can first annotate the animate method parameter 7 and 8 with pixels and second. Guided by the generated constraints box in red, PUnits will infer speed x to be pixels per second. The unit for DPI can be inferred as dimensionless, and the unit for mean speed can be inferred as pixels per second, or vice versa. Using annotation mode, the programmer can inspect the inference result and realizes that the solution says DPI is dimensionless. However, the intended unit for DPI is pixels per inch, which indicates that there is error. Note how this error would have been missed without a human looking at the inference result. Annotation mode is essential for enabling this use case. This is what the fully annotated source code will look like. The arithmetic constraint with pixels per second divided by pixels per inch gives inches per second, and the comparable constraint with pixels per second gives pixels per second or top. No solution will satisfy both constraints, and evaluation will fail because it's impossible to find a solution for placeholder 5. Type check will issue a comparison type incompatible error, and inference will evaluate to unsat. For the evaluation, we try to answer 3 research questions. What are the benefits and trade-offs of using PUnits versus existing Java unit libraries? Can PUnits detect and prevent unit-related errors in real-world projects? Is PUnits suitable to use in a real-world development environment? To answer these questions, we first provided the annotated JDK specifications for commonly used libraries. The benchmarks are open-source Java projects with scientific computations. Project Dietl contains a known unit bug. Project Gasflow uses JScience, which is a Java unit library. To answer the first research question, we replaced uses of JScience with PUnit specifications in the gas flow project. Then we run module type checking on the annotated code. We found 3 unit errors, whereas JScience failed to detect them. The reason why JScience cannot detect these errors are due to the use of unsafe casting and raw data types. In the example here, JScience allowed the assignment and the return of a value with a unit in the dimension of an area to an object in the dimension of a length. PUnits restricts such usage and issues type errors on unsafe unit conversions. Also, PUnit will not add any overhead to the program during runtime, since it is a static analysis tool. We were able to reduce the execution time and memory usage of running the gas flow project by more than 10%. PUnit was able to detect the known unit bug in Dietl, and we ensured that no other unit bug exists. For the other 6 projects with no known unit bugs, we used PUnit to infer and fully annotated the projects. If inference succeeds, we know the projects are unit correct. 3 projects reached unsat in inference because they contain heterogeneous arrays and methods. That means they did not prevent the user from passing in values of one unit into something that may expect another. These errors can lead to serious failures if the libraries were used incorrectly in critical systems. PUnit identifies such design issues and forces developers to restructure their program in a way that can guarantee unit safety. We fixed 2 of the 3 projects and successfully inserted the annotations back into their source code. The overhead for modular type checking mode is around 7 times. For inference mode is another 7 times slower than the type checking mode. For annotation mode is another 8 times slower than the inference mode. The performance of type checking mode is suitable for edit compile unit test development workflows. And inference mode performance is suitable for continuous integration workflows. Annotation mode is slow, but the mode is expected to be used less frequently. It can be used to provide well-specified applications and libraries. Overall, we think PUnits is suitable to use in a real-world development environment. This is the overview of the features provided by each related work. They differ in their expressiveness, how units are internally represented, how units are inferred, and how the annotation burden is reduced. The base units in PUnits are customizable, which allows non-SI units and dimensional analysis. No other unit type system have receiver-dependent types. To conclude, PUnits is an optional type system with a constraint-based whole program type inference. It is the first system that provides a practical unit of measurement type inference system. Our evaluation of PUnits shows that these techniques provide expressive and precise analysis with strong static guarantees. It strikes a novel balance between expressiveness, inference complexity, and annotation effort. Our approach and implementation can also be used to define other pluggable type systems and their inference. Thank you for listening. Please check out our material at oprop.github.io.